Hello friends. So today we are going to discuss questions from modern physics from the year 2019, and total questions are 15, and all these are from the mains. So first question, it states that the electron in a hydrogen atom first jumps from third excited state to the second excited state and subsequently to the first excited state. The ratio of respective wavelengths λ1 and λ2 of the photons emitted in this process is. So in this case, we are given that it starts from the third and jumps to the second, and the wavelength in that case is given as λ1, and then from second it jumps to the first. The wavelength is given to us as λ2, and we have to remember it is from the third excited state, so therefore value of n will be equal to 4, and we have this is second excited state, so the value of n will be equal to 3, and similarly for the other part also. So you can say we have third excited state, and this gives us that the value of n will be equal to 4, and it jumps to our second excited state, and second excited state giving us value of n is equal to 3, and under this process the wavelength is our λ1, and for the next it starts from the second excited state which gives us the value of n is equal to 3, and it jumps to first excited state. Value of n is equal to 2, and under this process the wavelength is our λ2, which we have, and ratio we are going to find out λ1 upon λ2. And here we are directly going to use the Rydberg formula, and we can say that Rydberg formula, which gives us 1 upon lambda is equal to r z square 1 upon n1 square minus 1 upon n2 square. And for hydrogen-like atom, this value of z is equal to 1, and we have λ1, so we can say for transition from n is equal to 4 to n is equal to 3, wavelength is given as λ1, therefore we can write it as 1 upon λ1 is equal to r 1 upon 3 square minus 1 upon 4 square, and this gives us 7 by 144 times r. Similarly, we can say that for n is equal to 3 to n is equal to 2. Under this condition, the wavelength is our lambda 2, so 1 upon lambda 2 is equal to r, and it comes as 1 upon 2 square minus 1 upon 3 square, and this gives us 5 upon 36 times r. Now we are supposed to find the ratio, and you can see lambda 1 upon lambda 2 will be equal to lambda 1 is our, this will be coming as 1 upon 144 times r, and lambda 2 is our 1 upon 36 times r, and our r and r cancels out, and this can be written as 5 upon 36 divided by 7 upon 144, which can be written as our 5 into 144, and we have here 36 multiplied by 7. This gives us 20 upon 7. So option number A is correct. Option A is correct. Next question. It states that an excited He1 positive ion emits 2 photons in succession with wavelengths 108.5 nanometer and 30 nanometer in making a transition to ground state. The quantum number n corresponds to its initial excited state is. We are given that our energy is in terms of 1240 divided by lambda. So we have 2 wavelengths, and we have to remember that we are given a He positive ion, and this value of Z is equal to our 2, and it says that transition is made to a ground state. Therefore we can say, and this transition to the ground state is in 2 steps. So we can write that transition to ground state, which basically is our n is equal to 1, is in 2 steps. And during these 2 steps we are having 2 wavelengths. Suppose first one is our lambda 1, which is our 108.5 and nanometer, and second is our lambda 2, which comes as our 30.4 nanometer. So therefore we can find that the total energy emitted, basic energy formula is given to us, that is E is equal to 1240 divided by lambda. So we have 2 wavelengths, therefore we can write that our total energy emitted let us call this as E total, will be equal to, we have this as 1240 divided by lambda 1 plus 1240 divided by lambda 2, and this gives us that our E total will be equal to 1240. We can take common, so this will be equal to our 1 upon 108.5 plus 1 upon 30.4. So we get this is approximately equal to our 52.22 electron volt. So therefore we get the total energy, or in simpler term we can also say that this is a representation of our E1 and this is a representation of our E2. And now we can use our nth energy formula, energy level formula rather. So we can say energy level for nth state is our E of n, which will be equal to our minus 136.13.6 multiplied by z square divided by n square, and value of z is about 2. Therefore we can write that our E of n is equal to minus 13.6 multiplied by 2 square divided by n square. This will be coming as our minus 54.4 divided by n square. And let us suppose the initial level is our n naught, final level we know is our ground state, that is value of n is equal to 1. Okay. So we can say let initial level is our n is equal to n naught, and final level we already know that is our ground state is our n is equal to 1. Therefore we can write that our delta of E will be equal to our ground state and our n naught state. And we already found out the formula for E of n, so we can take this is minus 54.4 as common, so this becomes 1 upon 1 square minus 1 upon n naught square, and this delta E will be nothing but our E total, so this will be equal to our 52.22 electron volt. And now it is simple calculation. You can say that our 1 minus 1 upon n naught square is equal to 52.22 divided by 54.4, and this will be coming approximately as 0.96. So from here we get our 1 upon n naught square is equal to 1 minus 0.96, which comes in as 0.04. Therefore we can say that our n naught square is equal to 1 upon 0.04, which will be over 25, giving us n naught is equal to 5. So we get n is equal to 5. Option B is correct. Next question. It states that in lithium 2 positive, electron in the first Bohr orbit is excited to a level by radiation of wavelength lambda when the ion gets de-excited to a ground state in all possible ways, including intermediate emissions. A total of 6 spectral lines are observed. What is the value of lambda? So here we are given that initially it is excited from the first orbit to a certain level, and then it's de-excited to the ground state, and total lines are observed, that is 6. And based on this we have to find out what will be our value of lambda. So we are given that we are having a lithium 2 positive, which gives us that the value of Z is equal to 3, and number of spectral lines are given to as 6. Okay. So number of spectral lines is over 6. So we can use the formula which gives us that number of lines will be equal to n minus 1 divided by 2, and this is our 6. So based on this we can find out that the value of n is equal to 4. So it means our electron is excited from the first state, value of n is equal to 1, that is our ground state, to the n is equal to 4. So you can write that electron is excited from n is equal to 1 to n is equal to 4. And we can find out the amount of energy required in this transition, and from there we can easily find out our wavelength. So we can say that energy required for transition and suppose that is given as E, then this E will be equal to our 13.6 Z square, and we have this as 1 upon n1 square minus 1 upon n2 square, and we already know value of Z as well as n1 and n2. So we get this energy will be equal to 13.6, value of Z is our 3, so this comes as 9, and we have this as 1 square minus 1 upon 4 square, and we get this energy will be equal to 114.75 electron volt. Now we can just convert, or we can say use the wavelength equation relationship with the energy. So we can say energy to wavelength, which gives us that our E is equal to hc upon lambda, or we can say our lambda is equal to h multiplied by c divided by e. And we already know these standard values. So we get lambda is equal to h is our 6.6 into 10 to the power minus 34. C is the speed of light, and energy we just found is our 1.75, and we convert into joules, so it is 1.6 into 10 to the power minus 19. So we get the wavelength will be equal to 10.8 nanometer. So option number C is correct. C is correct. Next question. It states that a helium-1 positive ion is in its first excited state. Its ionization energy is. So we are given that we are having a helium positive ion, and from here the value of Z is equal to 2, and it is in first excited state. First excited state, and this gives us that the value of N is equal to 2. We have to find out its ionization energy, and we can use directly the formula. We can say the ionization energy for nth level ionization energy for nth level will be equal to our E ion is equal to 13.6 Z square upon N square and electron volt, and value of Z is equal to our 2, and value of N is also equal to 2. So we get our E ion will be equal to 13.6 multiplied by 2 square and divided by 2 square. So 2 square goes away. This comes as 13.6 electron volt. So option number B is correct. B is correct. Or we can just find out our E also, and E and ionization energy are, you can say, without the sign. Answer will be same. Next question. It states that taking the wavelength of the first Balmer line in the hydrogen spectrum N3 to N2 is 660 nanometer, the wavelength of the second Balmer line N4 to N2 will be. So we are given that the transition is from N3 to N2, the wavelength is our 660 nanometer, and when the transition will be from 4 to 2, we have to find out its wavelength. So we can say that when the transition is from N to 3, to N to 2, we are given that the wavelength, let us suppose that is our lambda 1 is our 660 nanometer, and for the second one, when the transition is from N to 4 to N to 2, let us suppose the wavelength is our lambda 2, which we are supposed to find out. And we can just use the Rydberg formula and try to solve it. So Rydberg formula, it gives us 1 upon lambda is equal to r, and the Balmer series, we know that our final state is, that is value of n is about 2, and initial can be 3, 4 and 5, so on. Okay. So we can write this as 1 upon nf square minus 1 upon ni square. And we are given that we have Balmer, so we can say for Balmer our nf will be fixed, that is our 2, whereas value of ni will be equal to our 3, 4, 5 and so on. And therefore we can modify the Rydberg formula. We can write this as 1 upon lambda is equal to r, and this becomes about 2 square minus 1 upon ni square. And we have two wavelengths, one is of lambda 1, and in this case also our initial is 3, so we can divide this formula into 2, so we get 1 upon lambda 1 is equal to r 1 upon 2 square minus 1 upon 3 square, and this comes as our 5 upon 36 times r. Similarly, we can write for 1 upon lambda 2, which will be equal to our r 1 upon 2 square minus 1 upon 4 square, which will be equal to 3 by 16 times r. And we have to find out the lambda 2, or simply we can take the ratio, because lambda 1 we already know. Therefore we can say that our lambda 2 upon lambda 1 will be equal to our lambda 2 is our, this will be coming as 1 upon 3r upon 16, and lambda 1 will be equal to 1 upon 5r upon 36. So our r and r cancels out, so we get this as our 5 upon 36 multiplied by 16 upon 3. This is equal to, one second, 5 upon 30, yeah, this will be equal to our 20 upon 27. Therefore we can write that our lambda 2 will be equal to 20 upon 27 multiplied by lambda 1, and lambda 1 we already know, 20 upon 27 into lambda 1 is our 660, so this approximately comes as 488.9 nanometers. So we have option number D is correct. Next question. It states that radiation coming from transition n to 2 to n to 1 of the hydrogen atom fall on Hg1 positive ion in n1 to n2 states. The possible transition of helium ions as the absorbed energy from the radiation is. So in this case, energy is released from the hydrogen and that falls from on the helium. So first of all, we are going to take our hydrogen atom and try to find out the amount of energy that is being released. And the same energy will be absorbed by the helium ions. Okay. So you can say, and the transition is from N to 2 to N to 1. So you can say our transition from N to 2 to N to 1. Energy E is equal to, we have this as 13.6 Z square 1 upon N1 square minus 1 upon N2 square. And here we know that the value of Z will be equal to over 1 for case of hydrogen, and we get this as 13.6 1 square, and we have this as 1 square minus 1 upon 2 square. So we get the value of energy is approximately equal to, we can write this as 13.6, we need not to do the calculation, multiply by 3/4 electron volt. And we are going to make a comparison that this amount of energy will be absorbed by the helium ions, and we are given the various states of the helium ion. So based on this state, we are going to find out energy and make a comparison with the energy of the hydrogen. So we know that for helium 1 positive ion, value of Z is equal to 2. And first option is our from N is equal to 2 to N is equal to 3. So you can say our option A, we have our N is equal to 2 to N is equal to 3. Therefore, based on this, we can find out energy will be equal to 13.6 into 2 square, and we have this as 1 upon 2 square minus 1 upon 3 square, and we get the energy is equal to 13.6 multiplied by, this comes as our 5/9 electron volt. So obviously these two options do not match. Now we come to the option B, that is N1 and 4. Option B, N1 and 4, this gives us energy is equal to 13.6 into 2 square, and we have 1 square minus 4 square, and this gives us that our value of energy will be equal to 13.6 multiplied by 15 upon 4 electron volt, and this option also does not match. We come to the option C. Option C is our 2 to 5. So we have N is equal to 2 to N is equal to 5. So based on this, we get our energy is equal to 13.6 into 2 square 1 upon 2 square minus 5 square, and we get the value of energy will be equal to 13.6 multiplied by 21 upon 25. This option is also incorrect. So finally we are left with option D. Option D gives us 2 to 4. Value of n is equal to 2 and final value of n is equal to 4. So based on this, we can say our energy is equal to 13.6 into 2 square, and this comes as 2 square minus 1 upon 4 square. So we get value of energy will be equal to 13.6 multiplied by 3 by 4 electron volt. So this option matches with the released energy from our hydrogen. So option D is correct. Is correct. Next question. It states that a particle of mass m moves in a circular orbit in a central potential field UR kr square divided by 2. If Bohr quantization conditions are applied, radii of possible orbits and energy level vary with a quantum number ns. So we have to find out how the radii as well as energy level varies with the quantum number n. And we are given that we are having its potential energy is our given to us. So we can say potential energy that is our U of r is equal to half kr square, and this is a representation of a possible harmonic oscillator, because motion is circular, but it is some kind of oscillator. We can you can say that we will get to that conclusion later on also, as we are going to find out the force. So we can say the force F, which is our negative derivative of our potential energy. This comes as our half dr, and it will be half k r square, and this comes as minus kr. So from here at least we can see that our force which will be storing is proportional to the displacement, that is r. So it is just like a spring restoring force. And we also know that as it is moving in a circular orbit, so this restoring force will be acting as a centripetal force. So we can say that particle is moving in a circular orbit. This restoring force acts as a centripetal force. force. Therefore, we can write that our F is equal to mv square upon r, and we can just equate it with our kr, and from here we get that our mv square is equal to kr square. This is the one of the equation which we are going to use later on. Now we can use, because it is mentioned that Bohr quantization can be applied, therefore we can say that Bohr quantization so from there we can write our angular momentum L will be equal to mv r, or we can also write this will be equal to over nh upon 2 pi. So from here we can find out our velocity. We can say the velocity v will be equal to our nh upon 2 mr pi. So this is our value of velocity, and we substitute this value of velocity. Let us call this as equation 1 in equation 1. So we can say from equation 1 we get that our m, we have this as nh upon 2 pi mr whole square is equal to kr square, and we can just simplify it. We are going to get this as, let me square it first. We get that this is m n square h square divided by 4 pi square m square r square is equal to kr square. Here m goes by square, so we can write our n square h square will be equal to, this is about 4 pi square mk, and we have this as our r4. Okay. And so we are only interested in our the Bohr the quantum level, quantum number, sorry, and the value of n. Rest of things we can just ignore in terms of proportionality. So we can say our r raised to 4 is proportional to our n square, or we can say that our r is proportional to square root of n. So we get one of the options. So option A and B cannot be correct. Only option correct is our C and D. Now we are going to find out the energy relationship. So we can say the energy of the orbit let us suppose that is our E will be equal to our kinetic plus potential energy, and we can write this as our E is equal to our half m v square, and potential energy is already given to us as our half k r square, and we already know that our mv square is equal to kr square from equation 1. So we can say from equation 1 our v square is equal to kr square, or we can write that our half m v square is equal to half kr square. So we substitute it, we get this as energy E is equal to half k r square plus half k r square. This will be giving us our kr square. This gives us that our energy is proportional to our r square, but we know our r is proportional to our square root of n. Therefore we can say that our energy is proportional to our n. So therefore option C is correct. Option C is correct. Next question. We are given that in a hydrogen-like atom, when an electron jumps from M shell to L shell, the wavelength emitted radiation lambda. If an electron jumps from N shell to L shell, the wavelength of emitted radiation will be. So here we are just going to use a Rydberg formula and try to solve it. And for value of M shell, the value of n is equal to 3, L is giving us value of n is equal to 2, and we are left with N shell is our value of n is equal to 4. You can see that we are having our M shell, and value of M shell gives us that value of n is equal to over 3. Then we are having our L shell. So our L shell, the value of n is equal to over 2. And finally we have our N shell. For that the value of n is equal to over 4. And we need to find out the wavelength, so we can use a Rydberg formula. Rydberg formula, it gives us that 1 over lambda is equal to r z square 1 upon n1 square minus 1 upon n2 square. And first is jump from M to L. Therefore we can say that for M to L, we have 1 upon lambda is equal to our r z square, and this is our 2 square minus 3 square, which will be coming as 5 upon 36 times rz square. And next is our from N to L. Let us suppose that wavelength is our lambda prime will be equal to our r z square, and with the 2 square minus 4 square. This comes as 3 by 16 r z square. Now we can just find out the ratio. So we can say our lambda prime upon lambda will be equal to, and this will be equal to our 3 upon 16 rz square, and we have this as 5 upon 36 rz square. Rz square, r square cancels out, and this will be giving us our 5 by 36 multiplied by 3 by 16. This comes as our 20 upon 27. Therefore, we can write that the new wavelength lambda prime will be equal to 20 upon 27, the original wavelength, that is our lambda. So this becomes our 20 upon 27. Option C is correct. C is correct. Next question. It states that a hydrogen atom initially in the ground state is excited by absorbing a photon of wavelength 980 angstrom. The radius of the atom in the excited state in terms of Bohr radius A0 will be. So we are given as initial state, ground state, that the value of n is equal to 1. And let's find out our energy, and then we can move forward. So we can say that energy of photon that is equal to E is equal to hc upon lambda. Value of our hc can write 12,500 divided by 980, and this comes approximately as 12.76 electron volt. And we can also find out the energy for nth level. Energy for level n, that is E of n, is equal to minus 13.6 upon n square electron volt. And it states that the initially ground state, hydrogen atom initially in the ground state, initially it is a ground state and it is excited to some level. Let us suppose that level is our n. So we can say that atom absorbs photon energy E to jump from ground state to excited state. And let us suppose that state is given as n. Therefore, we can write that our E will be equal to our En minus E1. So we get this as minus 13.6 upon n square minus of minus 13.6 upon 1 square. This gives us 13.6, and we will say 1 minus 1 upon n square. And we need to find out value of n. So we can just rearrange it in terms of E. So we get this as 1 minus 1 upon n square is equal to E upon 13.6, or we get 1 upon n square is equal to 1 minus E upon 13.6, and value of E is our 12.76. 1 minus 12.76 divided by 13.6. This comes as 1 minus 0.938. So we get our 1 upon n square is equal to 0.062. So from here we get our n square is equal to 1 upon 0.062, approximately will be equal to 1613, giving us value of n is equal to 4. And we have to find out the radius. Okay, so you can say the radius of excited state that is our r of n is equal to our n square multiplied by Bohr radius a n naught. Value of n is our 4. Therefore from here we get our r of n is equal to 16 times our a naught. So option number C is correct. Is correct. Next question. It states that the stopping potential V naught as a function of frequency nu for a sodium emitter is shown in the figure. The work function of the sodium from the data plotted in the figure is. So here we are given that we have stopping potential as well the frequency. Okay, and we have to remember that our stopping potential for the frequency range of our 2 to 4 is equal to 0. Okay, it starts to increase only when our frequency is at 4. So we can just use the standard formula, and that standard formula is our h times nu is equal to our work function plus E times our stopping potential, that is V naught. From here we can write that our V naught will be equal to our h nu upon E minus phi upon E, and our stopping potential is having 0 value up till our frequency is our 4. So we can say from here that our V naught, or rather we can say from graph, V naught is equal to 0 for nu is equal to 4 into 10 to the power 14 hertz. So we can just substitute it. We get our stopping potential is 0, and this is our h nu upon E minus phi upon E. This gives us that our phi is equal to h times nu, and we already know all these values. So this comes as our 6.6 into 10 to the power minus 34, and frequency is 4 into 10 to the power 14, and divided by our 1.6 into 10 to the power minus 19. So this gives us that work function is approximately equal to 1.66 electron volt. So it is option B is correct. B is correct. Next question. It states that a 2 milliwatt laser operates at a wavelength of 500 nanometer. The number of photons that will be emitted per second is. So we are given a laser of power 2 milliwatt and wavelength is given. So first of all, we have to find out number of photons that will emitted, and for that first of all we are going to find out our energy, and then we can use the relationship between energy and our you can say power to find out the number of photons. So we can say energy per photon that our E is equal to hc upon lambda. We substitute the value, we get E is equal to, we have this 6.6 into 10 to the power minus 34, C is into 3 into 10 to the power 8, and lambda is 500 nanometer, 10 to the power minus 9. This gives us that our energy will be equal to 3.96 into 10 to the power minus 19 joules. Now we can just find out directly that number of photons emitted. Number of photons per second will be equal to power, and we have energy per photon. So we get this as 2 into 2 milliwatt, 10 to the power minus 3, and this comes as 3.96 into 10 to the power minus 19. So we get approximately 5.05 into 10 to the power 15. So we can say option B is correct. Next question. It states that one second. We are given that in a photoelectric effect experiment, the threshold wavelength of the light is 380 nanometer. If the wavelength of the incident light is 260 nanometer, the maximum kinetic energy emitted electrons will be. So we are given threshold wavelength as well as incident wavelength. So we can say that our threshold wavelength let us suppose that is given as lambda naught. Lambda naught will be equal to 380 nanometer, and we have incident wavelength that is our lambda is equal to 260 nanometers. And we can use our energy formula to find out the energy associated with threshold as well as our incident wavelength. So we can say that our energy of incident photon call this as E photon, will be equal to our 1237 divided by lambda, and from here we get our E photon will be equal to 1237, lambda is our 260, so this comes as 4.76 electron volt. And now we can find out the threshold wavelength, and in this case we have to remember that this threshold wavelength is a representation, or we can say our indirectly it is mentioned as a work function, because work function is nothing but our energy corresponding to threshold wavelength. Okay, we can say our work function phi, or we can say it as energy corresponding to threshold wavelength. And therefore we can say our phi will be equal to over 1237 divided by lambda naught, which comes as 1237, lambda naught is our 380, so this is approximately equal to 3.25 electron volt. Now easily we can find out our maximum kinetic energy. You can say maximum kinetic energy, let us suppose that is our K max, will be equal to energy of the photon minus the work function. Energy of photon is our 4.76 minus 3.25. Therefore we get our K max is equal to 1.51 electron volt. 1.51, option C is correct. Correct. Next question. 1 second. I did the previous one. Yes. Next question states that the electric field of the light wave is given by this equation. This light falls on the metal plate of work function 2 electron volt. The stopping potential of the photoelectron is. So we are given that our electric field is given to us, equation is given rather. Okay. And from this equation we are going to find certain parameters by comparing it with the standard equation. Okay. So first of all we are going to compare it with standard equation and try to find out the angular frequency and the frequency of the light wave. So you can say our electric field equation, and that equation is our E is equal to E naught cos of kx minus omega t. So 1:1 comparison gives us that our omega, that is our angular frequency, is equal to 2 pi 6 into 10 to the power 14 and from here we can find out our frequency, that is our nu will be equal to omega upon 2 pi, and 2 pi cancels out, so this comes as 6 into 10 to the power 14 hertz. So we were able to find out our frequency, and now we can just find out our energy of the incident photon. So we can say energy of incident photon, suppose that is our E, will be equal to H multiplied by frequency H nu, and let me write this is E photon EP, okay, because electric field is also our E. So we substitute value of nu and H, so we get our energy of our photon will be equal to 6.6 into 10 to the power minus 34, and this comes as 6 into 10 to the power 14, and we can convert this electron volt and whole divided by 1.6 into 10 to the power minus 19. So this will be approximately equal to 2.48 electron volt, and we need to find out the stopping potential. Work function is given to us, so we can write that our photoelectric equation gives us that energy of the photon is equal to our 5 plus E times our stopping potential V naught, and we need to find out V naught, so we can just rearrange it. We get V naught is equal to energy of photon minus phi upon E. This comes as energy of photon is our 2.48, and this comes as 2, and we have to remember this is in electron volt and E. Okay. So E and E going to cancel out, so this gives us is equal to 0.48 volts. So option number A is correct. A is correct. Next question. We are given when a certain photosensitive surface is illuminated with a monochromatic light of frequency nu, the stopping potential for the photocurrent is minus V naught by 2. When the surface is illuminated by a monochromatic light of frequency nu by 2, the stopping potential is minus V naught. The threshold frequency of the photoelectric emission is. So we are given two frequencies, nu and nu by 2, and corresponding their stopping potential. So we can say for frequency nu, we have a stopping potential that is our minus mu naught by 2, and for frequency nu by 2 we are having a stopping potential of minus V naught, and we can use, we have to find out the threshold frequency, and let us assume that our threshold frequency is given as nu naught. So we can use our photoelectric equation. We can say photoelectric equation that E multiplied by V is equal to our h nu minus h nu naught. And we can just divide this equation into two parts because we have two stopping potential. Okay, here V is our stopping potential. And basically we are given stopping potential as minus of V naught by 2 as well as minus of V naught. But this negative is only the indicative of the direction. So we are going to just consider the magnitude and solve it. So therefore we can write that for nu we get equation as E is equal to, and we have this as minus V naught by 2 is equal to h nu minus h nu naught. And we have our, for frequency nu by 2 we get E into minus V naught, and this comes h nu naught by 2 minus h nu naught. And we can just solve it. So from the first part we can write our h nu naught is equal to our h nu plus E V naught by 2. And from the second equation we get our h nu naught is equal to h nu by 2 plus E times V naught. And we just add them, or we can say we equate them rather, because our left side is same. So we get, let this be equation number 1 and equation 2. So we can say from equation 1 and 2 we can write that our h nu plus E V naught by 2 is equal to h nu upon 2 plus E V naught. And from here we get our h nu upon 2 is equal to E V naught by 2. Okay. From here we can say that our h nu is equal to E times V naught. And we substitute it back in either equation 1 or equation 2. So we can say from equation 1 we can write that our h nu naught is equal to our h nu plus h nu by 2. This giving us 3 by 2 h nu, and our h and h cancels out, therefore we get our stopping frequency is equal to 3 times nu. So option number C is correct. Option C is correct. Next question. It states that in a photoelectric experiment, the wavelength of the light incident on the metal is changed from 300 nanometer to 400 nanometer. The decrease in stopping potential is close to. So we are given two wavelengths. Let us suppose we have one wavelength lambda 1, that is our 300 nanometer, and we have another wavelength lambda 2, which is our 400 nanometer. And the potential that is corresponding to lambda 1 is, let us suppose, V1, and corresponding to lambda 2 is our V2. Therefore, we can say that decrease in stopping potential let us suppose that is our delta V will be equal to V1 minus V2, which we are required to find out. And we can just use our photoelectric equation and divide accordingly into two wavelengths. So we can say photoelectric equation we get our, this is EV is equal to H nu minus phi, or we can say this will be HC upon lambda minus phi. And we can write that our stopping potential V will be equal to HC upon E lambda minus phi upon E. So we have two potentials. So we can write this as, first V1 will be equal to HC upon E lambda 1 minus phi upon E. Second is our V2, which we get as HC upon E lambda 2 minus phi upon E. And we have to find out their difference. Therefore, we can say that our delta V is equal to V1 minus V2. We get this as HC upon E lambda 1 minus phi upon E minus HC upon E lambda 2 minus phi upon E. And phi upon E obviously going to cancel out. So we can take our HC upon E as common. This will be 1 upon lambda 1 minus 1 upon lambda 2. Now we can easily substitute the values. We get this as our 1240, and we have this as 1 upon 300 minus 1 upon 400. So we get our delta V will be our 1240 multiplied by, this comes as 0.00083, approximately 1.029 volts. So we can say option D is correct. This can be treated approximately as our 1 volt. You can say option D is correct. D is correct. So this completes all the 15 questions of year 2015, and this is our part 1. Part 1 for the year 2019. So remaining questions of year 2019 we will try to cover in part 2 and part 3. If required, we are also going to do part 4 also, and that will be covering mains as well as advanced. So this completes part 1 of 15 questions from the year 2019. Thank you.